There was the discovery of X-rays, which allowed people to probe the structure of atoms. There was the discovery by Rutherford of the structure of the atom, that the atom essentially consists of a central nucleus with orbiting electrons. All these discoveries started to contribute to a deeper understanding of the periodic system. And it's especially the electronic structure, the way the electrons are arranged in shells, and this is also associated with Niels Bohr, that have contributed to giving a physics explanation of the periodic system.
Another important development was the idea of atomic number.
When atomic number was discovered, it was realized that it was not atomic weight that was the correct ordering principle, but this other quantity called atomic number. It later turned out to be associated with the number of protons in the nucleus. It was the work of Moseley, who was picking up on a suggestion made by an amateur scientist, a Dutchman called Van den Broek. Van den Broek doesn't get much credit. One, because he was an amateur. Moseley acknowledged the role of Van den Broek when he began his papers by saying that he was doing this work in order to verify the Van den Broek hypothesis, that there is a number that characterizes every element. And he very quickly found that that is indeed the case. He used X-rays to do this. Had it not been for the discovery of X-rays, that work would have been delayed. And very soon it was realized, to pick up on the story of the electrons, that Bohr realized that if you think of electrons as being in orbits, a lot of things can be explained. Spectra of atoms can be explained, and the periodic table can be explained.
Experiments with particle accelerators discovered other subatomic particles, so that a complex picture of atomic structure emerged. New elements were discovered, including the previously unknown group of the noble gases. The rare earth elements were filled in, and synthetic elements created by Glenn T. Seaborg and his team in the United States, and by scientists in Russia and in Germany. Gradually, the periodic table has been completed. The quantum mechanical model successfully predicts why electrons organize themselves into shells and orbitals, which in turn gives the periodic table its distinctive shape and the elements their properties. Because of this success, physicists sometimes claim that chemistry is really just a subset of physics, and that all of chemistry can be reduced to quantum mechanics.
There's a lot of discussion these days about reduction, whether quantum mechanics reduces the periodic table. Well, first of all, historically it didn't happen that way. The periodic table came before quantum mechanics. And secondly, even if it hadn't done, you cannot predict the periodic table from quantum mechanics. In other words, you can't start from quantum mechanics and derive the periodic table of the elements. An even simpler example, the placement of hydrogen and helium in the periodic system, that criterion by which hydrogen is being placed in group 1 because of its one electron is not followed when placing helium in a group. If it were, we would have to place helium in group 2 of the periodic table, which makes very little sense chemically, although some people have suggested it quite seriously. In the so-called left-step periodic table, helium is placed in the alkaline earths. If you use the criterion of how many electrons are required for a full outer shell, hydrogen requires 1 electron, as does fluorine and chlorine and bromine. And so, on that basis, hydrogen could justifiably be placed among the halogens. You sometimes see periodic tables with hydrogen and helium that are simply omitted or allowed to float above the periodic table. To me, that's unjustifiable, because why should it be that hydrogen and helium are allowed to get away from the periodic law, as if they're British royalty or something that are above the law? Right? In a democratic society, all the citizens have to obey the law. So I think all the elements should obey the periodic law. In other words, there really is an objective best periodic system in my view. It may not have been found yet. So there is an objective answer to, does helium belong in group 2 or in the noble gases? It so happens that I favor hydrogen in the halogens and keeping helium in the noble gases. And whether one does that in a left-step form or in a short form or in a medium-long form, I don't get too excited about that question. That's a question of shape rather than a question of placement of elements.
Quantum mechanics alone can't decide the placement of hydrogen and helium. There are other issues that cannot be determined through quantum mechanics.
If electronic configuration does not fully determine the placement of elements, then there's still something missing from the claimed reduction of the periodic table to quantum mechanics. There have been some other suggestions as to criteria that will definitely settle the placement of elements. I've made one of them, and it concerns triads. These days we can use atomic number triads. If you take atomic numbers, sodium has exactly the average atomic number of lithium and potassium. Right? Now, so if you then apply that principle and ask the question, where should hydrogen be placed? It turns out quite conclusively that hydrogen should be in the halogens. I doubt that it's just numerology, because if there are so many triads in the periodic table, then perhaps there's something more fundamental. But we don't really know what that more fundamental thing is. Chemistry is usually thought to be due to the electronic structure. Now, since atomic number resides in the nucleus, this seems to suggest that somehow the nucleus is governing the chemistry. And this is radical. This has to be worked out.
Another anomaly in the periodic table is the so-called Knight's move pattern, where two elements that aren't in the same group but lie in a one-down and two-over relationship have very similar properties. One such pair is zinc and tin. Both are basically non-toxic. Both are galvanized onto iron to prevent corrosion. Both alloy easily with copper to form brass and bronze, respectively. Yet they are not in the same group and do not have identical outer electron configurations. Another pair is cadmium and lead. Both are poisonous, form brightly colored compounds, and are excellent for batteries. Silver and thallium, antimony and gallium are other pairs in a Knight's move pattern. No theory has yet been proposed to successfully explain these relationships. There have been many proposed periodic tables over the years. Some take familiar forms, such as the medium-long form we're used to, or the long-form table that places the rare earth elements in their proper position, but isn't as easy to fit on a printable page. Other people have proposed left-step tables, with the s orbital elements on the right and the other groups extended to the left. Other tables are more exotic, showing a continuity of elements as they increase in atomic number instead of dropping off at the end of each period. Other periodic systems use loops, spirals, and other intriguing shapes to represent the various families of elements. Some tables are even three-dimensional, and some are so unique that they resist classification. Some shapes are even similar to the strange attractor patterns found in fractal mathematics, and they become works of art as well as science. But in the end, the important ideas are that elements can be organized by properties into groups and by atomic number into periods, that the properties repeat periodically, and that most of the explanation for this comes from the structure of electrons inside the atoms of each element. For all the work that's been done on the periodic system, much still remains for students and historians of chemistry to explore.
I think there's still a lot of work to be done on the periodic table, of understanding the periodic table from a fundamental point of view. I mean, this is an endless quest, and the whole field of philosophy of chemistry is, in a sense, only just starting out. Over the last 10 to 15 years, there has begun to be interest in philosophy of chemistry. Somebody going into the field, I would say philosophy of chemistry would be a good area to go into. Certainly they would need courses in history of science, in philosophy of science, in regular philosophy, and in science, in real science, because you can't do philosophy of science without knowing science. So it's definitely an interdisciplinary area.
The periodic table of the elements remains one of the most recognizable icons of science. It is also an incredibly useful arrangement of information about atomic properties, and a central organizing principle for all of chemistry for unearthing the elements.